So on them 3 sheets I gave you this morning, the third one, I said there's not much different stuff on the third one than what you've got on the other 2. But one of the interesting things about it is the layout on it, and it's got layout like this, so it's got all the 3 dimensions. But for example, velocity, it's got m to 0, so there's no mass. Because what does anything to power 0 mean?
1. Nothing.
1, yeah, so it's not there really. So that's another way of writing it, that's all. Now the reason I show you that is because it's going to become relevant to what we're doing now. Sorry?
Is that your first open bracket or is it an L? Before
It's in the first open bracket.
Yeah, of course.
It's my... Is that better?
Yeah.
Yeah. Okay, so it's just another way of writing it. So we wouldn't normally bother, you wouldn't normally write that in, but it's going to become relevant to what we're going to do now, this deriving formula we're going to do. Okay, so let's have a look. Are you all comfortable with what we did this morning?
Yeah.
Except for...
No.
Right, okay, good, that's brilliant. That's good. You can always do another example or two if needed. Okay, so picture this, working a formula out. So we've got a pendulum. So now put it down in centre position. Pendulum on a piece of wire, rope, whatever, and it swings backwards and forwards. Okay, and this is radians, degrees radians. We've got mass for the pendulum. We've got length of the string. So L for the length of the string. And we've got this here. So if it started here, went there and came back, that'd be one cycle. We call that period. So it uses a capital T, the period in the formulas generally. But it's time, it's just another definition for time. So we're going to work out the formula. It's quite a famous, well-known formula actually, but we're going to work it out from first principles. So what we know is this. We'll use, so T is for the period. That's in units of time. So we're going to use that'll be our T in our dimensions. We've got the length of the string, or the chain, or whatever it may be. So that's in metres, and we're going to use length. What else have we got? We've got the mass. So that's our mass, which is in kilograms. And we use the M. Okay, and then we've got gravity, G. That's gravity pulling it down, so when it's swinging, it's pulling it back to the centre. When you do this, you've got to use a small angle, as you don't get a very precise value for your period, because it's you've got 2 forces affecting it. You've got the one pulling on it, and one pulling it down, and one pulling it out, the velocity. So G is gravity. So that's meters per second squared. So in hours it's going to be LT minus 2 in our dimensions. And the angle in radians is dimensionless. Okay, so it's dimensionless, so that's okay. It's not got any dimensions. Okay.
What's the radian, sorry?
It's a theta, Greek letter theta, yeah. We haven't got the Greek alphabet anymore in here, have we? Yeah. So it's a theta for Greek. It's what we usually use for the variable. But it could be degrees or it could be radians. We prefer radians. Okay, so we know a few things. We know that the period is proportional to the length We know that the period is proportional to the mass. Well, we don't, I say we know, we're going to find out. We assume it's proportional. And the period is proportional to gravity, to G. We assume. So we can rewrite that and we can say that T is proportional to these three, L, M, G. Which we can rewrite then and say this proportional, we can say that it has some constant, so it's equal to some constant, the length, the mass and the G. Okay, that probably should be a big M. I'm going to change that, because it makes it look like meters. The mass, okay, and G. So some constant will define, make that into an equal sign. We don't know what the constant is. And a constant could be 0. Like Ohm's law, there's a constant there, but not 0, 1. Could be 1. If it was 0, obviously it would annihilate the whole thing. So it could be 1. Could be pi. Could be just some number, like you often get in equations. So we don't know about that one. So what we're going to do is we're going to designate, we're going to say, we'll put an A, a B and a C above these three things. So we've got the indices, the power that applies to those three things, three terms. We don't know what they are. So A could be 0. So anything to the power 0 is 1, so that term will disappear, which we saw in that previous example with the M with a 0. So it could be a 0, so it disappears. Could be a 1, could be -1, could be 2, 3, could be anything actually. So it'll tell us something. So what we're going to do is find out what they are. So what we've got, I'll switch to blue. So that's me, I'll keep that information. So what we're going to say is, using dimensions, these, we're going to say that T, so that's the one for that period here. So it's in seconds, so it's a big uppercase T.
Sally, so what's that sign?
This one,
Yeah.
proportional. Proportional, so it's the result of the period's going to be as a result of the length of the string. We surmise. And it's going to be proportional. The mass is going to affect it because there's more mass. You've got more gravity pulling on it. So it's a fair assumption. And gravity itself, of course. So the stronger gravity is the more it's going to affect it. That's an assumption that could prove not to be the case with any of them, or all of them, or none of them. So we're going to find out really. That's what we're going to do. Once we've found out what A, B, and C is that, then we'll know. We'll have a formula. Okay. So we're going to use our dimensional analysis to work out what these are, A, B and C. That's the clever stuff that comes in. So we've got T equals, so we've got, I've done it same way, L for the length, and that's got an A. Just get this the right way around. Yeah.
What's next to that L?
It's an A. I'm going to move that to the outside.
Where have you got an A from?
Okay, what we've done is we've designated that each of these three terms has got some kind of index above it, of power. And we've designated them A, B and C, so we've got to find out what they are. That's the next challenge. They could be 0, they might not be there, and 0 would make, say that became 0, that would make L disappear because if it's the power of 0, which makes it 1, so the length of the string would be gone. So that would be implying that the length of the string makes no difference whatsoever to the period. It's quite an assumption to make, but that's the beauty of this, it does it for you. Same goes for B, same goes for C. It could be a -1 or a +1 or 2 or a half or 3 halves or something of that nature. We need to find out. So this is the A, lowercase a. Then we've got, so our M there, we've designated B, and then our acceleration due to gravity is LT minus 2, of course, and the power there is C. Okay. So what we then do is distribute the A's, the B's and the C's into our dimensions, and we're going to get, so T will equal L to the A. When it's on the outside like this, it's like your normal brackets, it applies to everything within inside. So that's the distinction there. Obviously I could have just put it in the first place, like I did start to do actually. But just to be precise about it, we'll put it in afterwards. So M, I missed it out, make myself some room. And then this would become L to the C, and then T to the minus 2C. Like that. So the next bit is the magic bit. Okay? The bit where you'll go, how does that work? We're going to equate the powers. So we're going to equate the powers from the left hand side and the right hand side. I don't know if you've come across this before. Equating powers, you can also equate coefficients and you can solve unknowns. It's magic. Okay? The reason it works is quite complex, but it just works. So you have to, it's one of them things you just have to, unless you want to spend a good few hours researching it, it's one of them things best taken at face value to start with at least, certainly now. So we're going to equate the powers. That means we look at the ones on the left and equate the powers to the ones on the right. Now on the right we've got M, we've got L's, but they don't exist on the left. But they do exist on the left actually, but they're hidden. This little step here is going to be nice. They exist like this to a 0, which is 1. So it's like a workaround. You don't have to put these in, you can just know this and work from it. But I'll put them in for the full picture. So we've got L to the 0 on the left, and then we've got T, which is to a 1. Obviously. Okay. Equals, so L to the A times M to the B, and then so we've got L, C and T minus 2C. Okay, going uphill a little bit there. Is that alright with that? I've got that.
So can you just quickly explain where you got M0, L0 and then T1?
These, right, okay, yes. On our left hand side they don't exist.
Yeah.
We've only got a T for the time of the period. But they do exist because anything to the power of 0 is 1.
Okay.
So that's why I showed you that at the beginning about the standard way of doing, well, one of the standard ways to write the formula where you put them all in. But we don't, it's just clutter, so we don't do it. So we can have them, we don't have to do this. This is just for what I'm going to do next to make it easier to follow. And then later on you might discard it. You know, when you do these things, when you write full amounts in and you just take shortcuts.
But so why is T to the power of 1?
Because it is,
It's already there.
yeah, we don't put the 1 in, do we? But everything,
Yeah,
you know,
yeah,
x,
yeah.
x on its own is to the power of 1, but we don't write the 1 in. And there's a 1 in front of it multiplying it, we don't write that either. So, we're going to equate, let's write that down, the powers. Okay. That's what we're doing now. So let's have a look. Let's start with, I suppose I'll go on your notes. So for M, we've got there, M's on the left hand side is 0. So we've got 0 equals, on the other side we've just got B. Now here's an interesting thing straight off. So on the left, on the right hand side, we've only got a b as a power. So b equals 0, 0 equals b. So we've already found out that mass actually makes no difference to the swing of a pendulum and the length of the period. Okay, we didn't know that unless you knew the formula. We do now. So that's interesting straight off, just like that. For L, the next one, we've got 0 equals A and C. So it's multiplying it, so it's going to be a plus. All the indices, C. So we don't know what either then is from that. So for example, if that was 1, that would be -1, wouldn't it? 1 minus 1 equals 0. I mean, that's about all we know, that one's the opposite to the other one. For T, we've got a 1 equals -2C. -2C. So now we're getting somewhere. That means that therefore, whoops, why have I written that in superscript? -1C, 3C, 2C, I'll get right in the end. Okay? Therefore, that means that C, for those who are not familiar with my method, that's your shorthand for therefore. Okay, the triangle of dots. Therefore, C equals -1/2. Rearrange that, we divide through by -2. We end up with that, C equals -1/2. Okay? Then, therefore, going back to this, A equals 1/2. Because 1/2 plus or minus 1/2 gives you 0, which is what we've got there. So we've now got A, B and C. Let's go back to black, and I find my top. Yeah, we need to make invisible tutors.
Is there going to be a therefore again? So therefore A equals to 1/2.
Yes, A equals 1/2, C equals -1/2, which is going to be a power, square root, and B equals 0. So we found our 3 terms. So let's put that there. So that means I can now take those numbers, put them back into our formula on Ne Presto. So we've got the period is equal to K, some constant that we don't know what it is at this stage. 8 L to the A. Now A is 1/2. Okay, I'll make it bigger than it should be, so you can see that. M is 0, so that's a 1, so it's basically times 1, so it doesn't affect it, it doesn't come into play. And then G is our acceleration, and that is a -1/2. Which I can write like this. T equals L, don't forget the K, L to 1/2 divided by G to 1/2. I nearly put minus in, 1/2, because it's -1, -1/2, so it's going to be on the denominator. Okay? Or, I can write it like this. I've just got enough room. L, make that a bit bigger than that. L over G. So our formula is this. Make it big. Okay, square root of L divided by G, which is just working that through the maths of that. Now that is actually a known formula. You can use that to work out the gravity, actually, the pull of the gravity on the Earth, or any planet you're on, actually. by just setting the pendulum swinging. Now it turns out, very logically, if you think about it, because it's a pendulum, so it's going out and back, it's a period, so it's a full sinusoidal wave in effect, so it's going to be 2 pi, because that's what a full waveform is, 2 pi. So k ends up being 2 pi. Okay, so that's pretty good from not knowing. Gives us something quite substantial. So if you've ever got a free afternoon when you're bored, you can get a piece of a weight on a piece of string, set it swinging, do a lot of swings, and then divide by the number you've done. So say you do 100, divided by 100, it'll tell you how long it's taken. You have to rearrange the equation, but you can then find out what G is. You know the length of your string, make it a metre long, for example. Do it in SI units. So we did it. We used to be what we used to do on one of the level 4 maths actually, and it's hard to get a precise answer. 9.806 it is a precise answer relatively, and it's hard to get a precise answer, but because there's too many things, the friction in the string and all sorts of things interfere with it. But the trick is to do a lot of swings, because trying to time it as well. Time 1, you've no chance. Was that 1.2 or 1.3? But if you do, say, 100 or more, you can time it and then divide, so it removes your error. It's good fun, honest. Okay. It's quite interesting if you get it near. When they do it for real. This is how Galileo, allegedly, this is how Galileo worked this out. He was watching. He was in the church in Rome or wherever, and he was watching the light swinging, and it led him to. Huh? What's a Galileo? Galileo. He's going to start singing soon. Yeah. It was one of the.
Does it G to the power minus half or just half?
Right, it's a half there, minus half there.
Yeah.
But that means it's actually a divide term.
Alright, because
X to the minus 1, for example, means 1 over x. So, and it's a square root. So if I rearrange it, I get this basically, which leads to this. So what the other thing we need to do, so Galileo, whoever did this initially, would have to check that it balances. So it's the same thing as before. Okay, so we look to the left, we've got, we'd have to go put these numbers in. We know that this was 0 on this side, so that would agree. This was a half, wasn't it? A plus and minus a half, so they're going to cancel out. And then we've got t minus 2c, and c was a half minus a half, and it's minus a minus makes it a plus 2 times. So we end up with 2 halves, so then it would back being 1. So it agrees with that. Did you follow that? I was a bit fast there. There's m's at 0 because it's b equals 0. L is a and c, so that's plus and minus halves. So add them 2 powers, you get 1. Do that right, Kevin. Where are we? I've lost myself. Yeah, that's right, because we haven't got one on the left hand side, correct? Yeah, sorry, so they disappear. And t is minus 2 times c, which is a minus half, so the 2 minus make it a plus, so you'd end up with a 1, a positive 1, which agrees with that. So it's balanced, in other words.